Hi. So I left off last time, once again, promising to talk about calculus and functions that can mathematically model physical reality for us, because that's ultimately what physics is about. It's about ways that we can describe reality such that mathematical modeling is possible, because over the course of human history, we've developed a great many mathematical tools that are extremely useful. And we want to basically be able to do things like, well, predict the future, right? And in physics, we're able to do that because we constrain ourselves to predictions that are very simple, like where objects will be in space at particular points in time. And so to do that, we have different ways of measuring things. Like we measure space with things like rulers, right? Where we just, see how many, lengths of a particular ruler fit in a given space, like 1, 2, 3, 4, and so on and so forth. And we do the same thing in time with something like a pendulum, right? We let a pendulum swing back and forth, and we count 1, 2, 3, 4, 5, and so on and so forth. So how do we start putting that together to start talking about something that's actually mathematically useful? Because it seems like we've been going very slowly and talking about a lot of very pedantic philosophical concepts. And that's in part because I like thinking about those things, but it's also because now we're going to start using that to construct some very useful mathematical tools. And so if you'll recall, we're talking about this simple problem of you have an object that moves forward in space, right? It starts at one point in space at a particular point in time, or actually I have this little clock diagram, and then it starts at another point, and then it ends at another point in space at another point in time. And so we want to describe that process mathematically, and so we define these things like velocities and speeds, which for now are going to be essentially the same thing. And they describe how an object moves through space. So last time we were discussing this simple concept of me driving my car and it taking a particular amount of time to travel a particular amount of distance. And so I keep talking about this concept of sort of precision and resolution and like how much do you zoom in on a measurement, right? Do you just use a ruler, or do you zoom in on? Oh, sorry, those are the inches. You could zoom in on the inches too. Remember, you can use whatever units you want, but metric units are just generally going to be a lot more convenient. And so, but you can zoom in on the centimeter sections, or you can zoom in further and you can start looking at the millimeter sections. But then, with this ruler, you start running into a problem that it only goes down to millimeters. And with something like this, it's even worse, right? Where it's like, in between when it, as if I count every time it reaches, back to this point over here, well, that's going to leave me with if situation where any time that an amount of time I want to measure ends, like, say instead of, the amount of time I want to measure doesn't end when it's perfectly up here, it ends when it's right in the middle, or it ends when it's here, how do you deal with that? Well, so experimentally and dealing with data, we deal with it one way, and when we're dealing with mathematical modeling, we deal with it another way. And they're ultimately related to the same concepts, and I'm trying to tie those things into each other a little bit, because calculus is not like other areas of mathematics. Most areas of mathematics are invented because of mathematics itself. And calculus is unusual in that it was invented to deal with physics problems, and really to deal with the invention of what we now call physics by Isaac Newton. And of course it was also developed in parallel by Leibniz, working on very similar problems. But it was invented for the same reasons. Leibniz did not go as far down the sort of physics rabbit hole, and in turn he went down more sort of pure mathematics and was able to develop sort of better notation and machinery than Newton was. And Newton, in turn, then was able to sort of take his discovery, even though it was made independently, and apply it to this problem of describing motion in detail. But Leibniz was thinking about somewhat similar things, right? Of how do you describe these things that are clearly what we call continuous, right? Where it's like objects are discrete, right? One object, two object, versus distances are continuous, right? It's just however far it is. So how do you deal with that when you have something like this, where you're, say, going 60 kilometers an hour, which is about 40 miles an hour, which is roughly how fast I was driving in the data from the previous video. And so then I want to ask, how far do you go in 15 minutes? Well, okay, that's pretty simple. 15 minutes is a quarter of an hour. You're going 60 kilometers an hour. It's 15 kilometers. Okay, well, that's all fine and good, but, well, what if you're only going 30 kilometers an hour and you go for 15 minutes? Well, now you've gone 7.5 kilometers, and you have to deal with more decimal places, don't you? So, experimentally, this is not terribly dramatic. I uploaded a tutorial on significant figures, and we're not going to deal with error propagation or uncertainty just yet, but we are going to start worrying more about significant figures because we're starting to think about what they mean. Because the reason that you specify here... I held up some data last week that was actually inaccurate, but close to accurate, so I'll hold up the more accurate version shortly. Which, the reason, by the way, is I'm trying to make a bold commitment to getting the physics very, very accurate, but I very much am learning how to edit videos, and I'm not good at that yet, so please bear with me on that. If I get the physics wrong, call me out on it right away, and I will promptly fix it, but my video editing skills, please try to bear with me. So, but if you go back to the previous video and look at the data section and write that down, which is an exercise you should do, but of course I've done it for you because I'm doing these lectures. I have to certainly do the exercise myself, and also we need to now continue forward with that data. So what's going on here? So this is the land before time over here. This is where, you know, I was doing something, but I wasn't taking data on it, and so I'm not going to try to model it mathematically. And so down here is the data table. So I've written down for you the distances and the corresponding timestamps, and then I've graphed them. And so what you'll see here, though, is notice that there's these data points, and there's this red line, and there's also that dashed line connecting them. Right, so what's going on is, what's that red line? Well, that red line is a representation of my average speed. So my average speed, remember, is just the total distance divided by the total time. It does not tell you how fast you're going at any given instant, which is your instantaneous speed or instantaneous velocity, if you're going to include directionality. It's just how far do you go after a finite amount of time. And the astute amongst you may quickly realize that, well, you have to measure a finite amount of time, don't you, right? These data points are not infinitely close together. They are always going to have some finite distance between them because we have a finite amount of resolution to our measurements. And that's sort of the reason that we do significant figures, right, is we want to basically keep track of the resolution of the mathematical answers that we have based on the resolution of the instruments that we started with, and so that we have a representation of how precise that information is. And so there's two issues. One is just sort of keeping scientifically rigorous account of the information we're describing from experiments, but because we're also dealing with this question that I'm going to come back to in a moment of Zeno's paradox, we have to think a little bit about, we can only measure so frequently, but what happens in between, right? Because you see, that red line is a pretty good representation of the speed of the car, right? You see that down here it maybe deviates a little bit as I'm slowing down in a couple of places, but not by much, right? And but nevertheless, then that behooves you to wonder, well, if that red line is just the average velocity over 2 minutes, and then each of those dots is actually just the average velocity or average speed over approximately 10 seconds. So, well, what about in between those 10-second intervals? Well, we didn't measure anything, but it's not like I popped out of existence, did I? At least as far as I know. And so, if we want to model reality mathematically, we have to come up with a way to account for that. And so, let's go back to this sort of graphed version of Zeno's paradox, right, where we're imagining going a certain amount of... This is not the data from driving my car. This is some made-up data. So Now imagine again, we're zooming in instead of actually taking data points, we're just imagining them, closer and closer to the origin here, because, well, time equals 0, the process had to start at some point. Achilles does at some point start running and pass the tortoise. So now, well, what do we do experimentally? Well, experimentally we do one of two things, right? We do either extrapolation or interpolation. So in this data that I'm showing you from driving my car, which this data is graphed by hand, and if you want to learn how to do that, take an algebra class, But if you want to learn how to do that in Python or Octave, which is a open source equivalent of MATLAB, I will upload a tutorial later this week on how to graph data like this using a programming language and sort of data analysis software. But I think there's a tremendous value in just graphing it by hand, which everybody should remember how to do from middle school algebra, and you should practice doing with this data from the previous video. But so now, okay, we have that data graphed, cool. Now what? Well, now we want to ask questions like, well, what happens after the end of our measurement interval, which is what we do if we extrapolate, right? We say, okay, well, probably it just keeps going, right? We don't know, but it's a pretty solid guess that it just keeps going. Now, something like driving my car, we know that prior to time equals 0, I was stopped at a stoplight when I reset my odometer and taped the phone to the steering wheel and all that, and pressed record. And then, well, okay, then after that, I also kept driving, although, of course, eventually I reached another stoplight and stopped the car and stopped the recording. But, well, okay, so we can probably extrapolate, but not necessarily, and that's definitely a lot of what we want to do, right? Because that's kind of what this is what physics is, in some level, all about, right? Is we have some data points that tell us what happens in time, and we want to ask ourselves what happens at some point in the future. But we also want to ask ourselves this question of what happens in between our data points. And that's called interpolation, right? And so, in between, it's just a bunch of question marks, and we don't know. But it's a safe bet that we can just kind of draw a line in between the data points, and it's somewhere around there, So, okay, but let's maybe try to get a little bit more sophisticated, and let's abstract ourselves away from any specific data set, although we definitely want to ground ourselves in thinking about data sets, not just thinking about math by itself, although I do enjoy pure mathematics. Physics is about grounding our understanding of reality using mathematics, not going down the rabbit hole of pure mathematics away from reality. As much fun as that is, and as much as it leads to these tools of mathematics that we're able to use, but we're focusing on physics here. So, okay, now let's start using something like a mathematical function. F of x equals y. And let's think about a simple function like this. Y equals some constant, which we'll call a, times x. Which, that's a pretty good model for something like this, where we're modeling something just traveling in a straight line, which at a constant speed. So, okay, cool. Now let's have a mathematical model. Well, all right. So, now let's define mathematical functions. So, all right, we say distance is some function of time, just like y is some function of x. Cool, very simple. And then, okay, that seems like kind of confusing, right? Y, x, t, what is anything? Well, we're going to try to be consistent with our notation. One thing is, actually, I mentioned that I'm going to continue to graph time on the horizontal axis, because I'm an experimentalist, so I'm used to using things like oscilloscopes, where time's on the horizontal axis. A lot of theoretical physicists will actually graph time on the vertical axis, so I'll do that sometimes when I'm doing certain types of theory calculations, but generally I graph time on the horizontal axis. So, but then what about the symbols? So, okay, t is generally going to be time. D is generally going to denote a distance, which is going to be a scalar, not a vector, although don't worry too much about that for now. But, you know, we're going to play fast and loose with our what variables we use to define space and distance. Generally, it's going to be something like this, where we're going to use x with a vector to mean, like, this kind of position. But, you know, x, y, z, d, we'll just specify, right? We just specify in the context of whatever problem we're solving. The only really consistent thing is that t is going to be time. Generally, it's going to be x is horizontal, y is vertical, t is time, and z is like the other axis, but sometimes z is vertical and x and y are horizontal, so, you know, there's no terribly consistent thing other than t for time. So, but now, what if you want to describe more complicated motion, right? What if you want to describe this mess I was describing a couple lectures ago, right? Where instead of maybe just going forwards, you know, first you go forwards and then you go backwards and then you start going forwards again and you go through some complicated process, or you can't maybe necessarily model it as just a straight line anymore. Well, now we start to graph things like this, where when we're missing information, now in here we're missing information, we're really missing information, right? Because it's not just a question of like, oh, okay, the data's all on a straight line, it's probably just, you know, adjacent to that line. It's like, no, you know, we know it's going all over the place, and also we know that we're missing data from the beginning. So you know, well, what's going on? Well, the answer is we don't know, but we know that something is happening. So if we want to say that our mathematical model is a description of reality, it has to have some accounting for what's happening in between. So, well, let's go back for a minute and look at what are the functions we could use to describe motion, because we know it's more complicated than just moving in a straight line. So, okay, well, what are all the functions that we learned? So, in, you know, typical algebra class, you learn things like polynomials, right? In just middle school algebra, you know, we could say that something is proportional to the time squared, the time cubed, the time to the fourth, something like that. We also have things like trigonometric functions, sine and cosine, have things like exponentials, all of which are extremely useful. And we would like to be able to use to model reality, but these are not a constant, right? These are not straight lines. And so if something is not a straight line, how do we get a handle on the speed, right? Because I told you that we want to calculate the instantaneous speed, you need to know the distance that something travels instantaneously, don't you? And, well, in one instant, it's not going to travel anywhere. So how do you deal with that? And also, if it's not traveling in a straight line, how do you define speed at other points, right? Because that's kind of a whole other problem. Because on this line, it's pretty easy. You just say, okay, well, you know, draw a line on each data point, and you say, you know, you go some distance, which is just 0.1 miles. It takes a certain amount of time. It's just you know, take one timestamp, subtract the previous timestamp. So say I get to 0.5 miles at 1 minute and 0.4 miles at 46 seconds. Okay, that's 14 seconds to go 0.1 miles, and then, you know, multiply that by 3,600 to get the speed in miles per hour. You get something that's roughly 40 miles per hour. Okay, cool. But, you know, what if my speed wasn't constant? Well, then there'd be some ambiguity in there, wouldn't there? I wouldn't be able to just say, okay, well, it's just this line anymore. So then how do we ask ourselves questions about, like, how fast something is going for a more general function? Because let's imagine that we want to model something with these two simple mathematical models, right? We could use d equals to 2 times t, so that would be moving at, you know, say 2 meters per second. And, you know, okay, so then at t equals 1, it's, you know, 2 meters. At t equals 2, it's 4 meters, and so on and so on. And the speed is just constant. It's just 2 meters per second. Simple, right? It's a constant ratio between the numbers above and below that line, right? Now let's try this d equals 2 times t squared model. And so then, okay, so here 2 is our speed, but down here is 2 also our speed? Well, here, you know, 8 divided by 4 is 2, 6 divided by 3 is 2, okay, cool. You know, but here, you know, t squared, you know, it goes, instead of just going up proportionally linearly, it goes 2, 8, 18, 32, and it goes up quadratically, right? So, you know, now we can't just divide the distance by the time anymore. And we're going to need to do something like this, right? where we just go in and we look at the slope of these smaller lines in between. But now we're using a mathematical function instead of data, so we can put data points wherever we want, right? We are no longer constrained by where we actually took data. In fact, in some sense, it's both better and worse than that. We are obliged to account for the points of space and time that we did not measure, because we know they must exist. So if we are modeling reality mathematically, then we must have some account of what is happening in between mathematically. But then that turns out to be very useful in resolving Zeno's paradox. Right? How does how does Achilles ever pass the tortoise if the tortoise starts out ahead of him and he has to get halfway there before he gets all the way there, and he has to get a quarter, remember, he has to get a quarter of the way there before he gets halfway there, he has to get an eighth of the way there before he gets a quarter of the way there, and so on and so on and so forth. And it's like, okay, well, how do we deal with that? Well, the answer ties into what I was talking about. Remember, there's two types of numbers. There's what we call countable infinities, which are discrete numbers like fractions and integers where you can count to them. And there's continuous infinities like this, where it's, well, continuous. And, you can zoom in, you can just keep zooming in further and further on the number line, and you never run out of numbers. Versus this, you keep zooming in, and it's like, whoop, there's 3, there's 4. And in between, well, there are numbers, but they're no longer integers. They're these continuum numbers. So then remember what I was saying a while ago about this question about, is 1 equal to 1, right? 1 plus 0 plus 0 plus 0 plus 0, right? What level of precision is enough? And so we are going to now, finally, after all this time, define actual calculus for ourselves and define something called the derivative. Which, if you're clicking on this video, it's probably because you wanted to learn about derivatives. But we're going to learn about them in a physics context because this is a physics course. So, let's define d by dx and call it the derivative. And we're going to write it in all these different ways, but we're mostly going to write it this way, which is the way that Leibniz wrote it. And it's because it tells us what we are taking the derivative with respect to. We call this taking the derivative with respect to x, or d by dx. So what the heck is that, right? Why did I define this whole new mathematical operation? We have gotten by just fine all our lives on, what? Addition, subtraction, multiplication, division, exponents, and square roots. And that's all we've ever needed. Why add some contrived new thing? Well, because of this thing I just mentioned, that if we're modeling reality mathematically, we can zoom in on our model as much as we want to, right? And x is not an integer, because time and space are not described by integers, are they? Because it's very rare that something is exactly 1 foot. So, why not make use of this? And 2, we are sort of philosophically obliged to make use of this in order to understand what the speed of an object in between our data points is, right? And so if we only wanted to evaluate, like, what is the average speed in between integer time points, we could do that just fine, but that's clearly not a model of reality, is it? Because most processes don't line up perfectly, right? Very seldom does something take exactly 1 day, and so that's true all the way down to 1 nanosecond. And so our ability to keep zooming in is now very useful. So now remember I was talking before, so there's this linear function where we keep zooming in and it's the same every time. So it's kind of like I was saying, if everything was just moving in a straight line at a constant speed, who cares, why bother? But reality doesn't work like that. Things move around in complex patterns, and we want to describe them, and they look something like this, right? Where this is a parabola, y equals, some constant times x squared, and there, if you zoom in more and more and more, you get something that looks more and more like just a flat line, actually. And so, well, what are we going to do with that? Well, let's now define what this thing called the derivative actually is. So the derivative is defined as the limit that this quantity called delta goes to 0 of f of x plus delta minus f of x divided by delta. So what is that? that is exactly what it sounds like. It's taking it back to something like this data that we actually graphed. Except it's saying, what if the distance between our data points was shrinking all the way to 0? Because that's what this delta is it's very much like the distance between our data points. Except because it's mathematical, we can shrink it to be as small as we want and ask ourselves what happens. And we ask ourselves, how fast is if something were, say, described by this simple function, and we wanted to know how fast it was going at some point in time, well, what do? We just take the average velocity, and we take it over a smaller and smaller interval, until eventually we're taking it over an interval of length 0, and then we have the instantaneous velocity, wham, bam, done. But it's much more powerful than that, because we've now invented something that can tell us that information, not for data points, but for mathematical functions. And that is going to start letting us do some really interesting things that we are going to start talking about in more detail next week. And so I am not going to get into it for today because we want to limit our calculations. But this is then the simplest example of if we want to start taking the derivative and applying it to these simple functions. And just spoiler, the derivative applied to this function b times x squared is 2 times b times x. And you can see the math for it there, and we'll explain that next week. But it always comes back to something like this, where we have these data points, and we want to measure these little local lines that tell us what the speed is at each of those data points. But we're doing it mathematically. And so this seems a little bit contrived right now, maybe, but I really want to tie it into this data set. And so we're going to start analyzing next time how to relate this concept of the derivative to fitting data with a line like this. And yeah, gonna keep exploring this in more detail. And like I said, I'll try to upload another lecture this week on how to plot data using Python and Octave and stuff like that. Because again, I would really encourage you to go back to the previous video, watch the data section, and plot the data by hand. But I will also do a tutorial later this week on how to plot data in various pieces of analysis software. So yeah, thanks for watching.